Today's PrimaVera Colloquium. So we're very happy that today we actually have two speakers, namely Bart Pollmann and Wieger Tiddens, who both work for the Dutch Netherlands Navy as innovator smart maintenance. So yeah, we're curious to your presentation of today. So if you are ready, please go ahead.
Yeah, ready. It's a co-presentation. I'm Bart Pollmann. Wieger Tiddens is standing next to me. I will do the first half of the presentation. We will pick on in the second part of it. I will do the general part, and Wieger will explain about the results we have achieved so far, and some questions we have for the future for PrimaVera. Because PrimaVera, we like to be part of it, and we have a nice interaction with the students and staff. Our presentation is about the smart use of sensor data, which is probably not surprising, but I can explain a bit more about our aim as Royal Netherlands Navy, and we want to achieve a more modern maintenance method for modern ships. Before I do that, just a few words about what is the Royal Netherlands Navy. It is the Maritime Defence Force, but it's not only what we do in the harbour in Den Helder. The operations take place from Den Helder, but we have important supporting activities, for instance, procurement in other regions, and the headquarters for that is in Utrecht. In total, Royal Netherlands Navy employs about 10,000 people, and we think that innovation is important because of the future build programs. Here are a few pictures of maintenance activities, and we show those two pictures especially because we operate both in the sensor equipment, radars and that sort of systems, but also in diesel engine and more mechanical systems. And for both, we would like to develop into a more predictive maintenance form. We're working from a small team from various sub-organizations in the Navy. Well, you may have seen Wieger and me. We're also working with Dennis and Jan from Den Helder. But very important, the DMO, the Defense Material Organization, which procures our new ships, they translate our requirements into requirements which are being sent to the industry. And we also cooperate with the industry to be on the same hymn sheet on system development. So that's Renze Geertsma and Shadia Shanessas. Within defense, we also have an IT supplier, that's the JIVC, and a knowledge center, the Royal Netherlands Naval College, the KIM, with Professor Tito Tinga, who is also participating in PrimaVera. The main aim, as I told you, is to improve the maintainability of our future ships, and replacement of the M-class frigates, which is about here. You can probably see my mouse. We'd like to have better data analysis facilities to support the crew. The ships tend to become a lot more complex, and crews are getting a lot leaner, fewer people on board of the same ship. So we need better support mechanisms to keep them in service and to increase the availability of the ships. The orange dot you see symbolizes the acquisition of data from sensors, the pre-processing of the data, the acquisition of the analysis of the data, and the production of maintenance advices for the crew. At the moment, we are piloting on current ships, and we've installed on one ship an extra server and some extra sensors to experiment with that, to try to get the best requirements for the future ships. And as said, we do that with the DMO, Defense Material Organization, but also with industry. This also comes from the Defense Vision 2035. It's a slide in Dutch. I'm sorry, but it's a Dutch document. But what's important is that we want to go into information operations, and not only for the operations itself, but also for the supporting activities such as maintenance. What I want to highlight is that we think that it stays human-centered. We need domain knowledge about mechanical and electrical systems to interpret all those advices. We don't believe yet in activities where data science is giving you the total solution. Some on the strategic aims of the Royal Netherlands Navy. The DMI, which is the Directorate of Maintenance, wants to have a better grip in the future, better control of the maintainability. We often got ships, and afterwards we said, well, we would like to have another service manual, and now we want to be on the forefront of defining the requirements. To support the ship crews, to have optimal availability, to enable autonomous operations, because we need to be away from need to be able to be away from home for at least 30 days, and the ports we can then visit are not always logistic support bases, but maybe it's only a small harbor. And we need to start early because it's relevant during the complete life cycle, which means even before the build of the ship, already in the design phase, in the in-service support phase, and also when we dispose of the ship in the end. What is our roadmap? This is part of our roadmap. We started in looking at what do we have. We do have sensors for monitoring and control. See it as the speedometer in your car. You can't drive safely if you don't have an indication of speed, for instance. We have a lot of those sensors in ships. Something we also already have since decades is vibration and fluid analysis for failure prediction to improve maintainability. But the interval between measurements is often about 4 months. So what we'd like to do is to get a better correlation between the two and use available sensors for monitoring and control as a sort of side effect for failure prediction. We also look at failure mechanisms which we want to detect, and they are not always detectable with the sensors we already have installed. So we're also thinking about additional sensors which you need to improve this failure prediction. Having done so, we also can combine with other data than the data we had initially in mind with the sensor data, the temperatures, pressures, etc. There's ERP data, open source data, like the weather, etc. And we also get more benefits from adding this data. For instance, you can look at fuel saving and less CO2 emissions. And for instance, operational optimization, so that you use the assets, the ships, better than we do now. Lots of opportunity enabled by data science. I told you a bit about extra sensors. What are we thinking about? For instance, more continuous measurements in terms of vibration and online fluid quality measurement, so that there's a better buildup of trends, power readings, fluid flows, because you can't detect anomalies in pumps if you don't have an indication of the fluid flow or power, cylinder pressures, etc. Important is IoT. The industrial IoT is an enabler to get this done. In the previous era, we had to wire all the sensors to a specific cabinet, and now it's all more part of a network, which is easier to install. And as I said, the use of the correlation between the sensor reading is very important. What we're working on is actually not a new idea. It's an idea from 1992, but after a lot of defense cuts that got into the bottom drawer. But since 2019, we picked up on the idea, and we have made a sort of basic platform on which we can analyze the data we have, and we're now growing up, which also gives us a growth paradox, because now we go into the bureaucratic planning processes, and we need to solve this to enable acceleration in the future. We think that's going to happen. We're not monitoring the data of all the fleet yet. We started with the green banner, the OPV Holland class, 4 ships. But we want to expand to all the other ships, and the yellow parts are ships we are now developing on and getting some of the data on. But in the end, this needs to be a green flag, say. One of the enabling factors to get additional data is a social behavior program, Oceans X. You may have heard of it. It's started in the Navy, but they try to use social constructs to stimulate crew to change their behavior in a good way. And one of the sub-programs of Oceans X is to use less fuel, to emit less CO2. And to measure this, if you compare the different ships, you need data, and we collect the data for them. So we have a sort of symbiosis with Oceans X, and well, we get more data, and they are being enabled to run their program. On the right bottom, you can see one of the most modern radars. We're also working with the industry to improve sensor data analysis on non-mechanical systems, because so far, because monitoring and control is more available on mechanical systems than electrical systems, the focus has been on the mechanical side. Short slide on the data pipeline. It's important to understand before you start analyzing. We got a ship, and there is data on this ship. But this data is unstructured. It's a file per day. So if you want to analyze a year, you need 365 files, and to combine those in a rather odd way. So you need data processing. We call that extract, transfer, load process, and get it into a proper time series database, data warehouse. Then we can start analyzing, and that's something we can't do on our own. We need the maintenance engineers of the DMI to help us. We help solve their problems. If they have a defect, we can help them analyze the data on relevant sensors to develop prediction. And Wieger is going to explain a bit more on that, because that's the result side of the presentation. And in the end, as I said, we do it for the maintenance engineer. We provide an extra tool for the maintenance engineer. We'd like to develop to prescriptive analytics. That's not where we are now. We started off with descriptive analytics, understanding the data, that sort of thing. And we're now carefully developing into diagnostic analytics. Again, that's part of the result. Wieger,
So thank you.
I think it's your turn.
Thank you, Bart. I will go back one simple slide, because I will show some results, what we are working on now. And these results are mainly in the descriptive phase. So we try to give insight to the maintenance engineers and the crew in what is being done in the machinery. So how is the ship used, and how can you maybe improve that? And with that, we hope to go to the next step where we can indicate what is wrong with the equipment and how we maybe can solve it. So we often want to go directly to predictive analytics, but we are quite sure that we really should start with the descriptive phase before we move ahead. So one of the first things we can do is give insight to the crew in how the diesel engines are used. So for that, you can, for example, use a power envelope. And we have now a tool available, which is available for all the maintenance engineers, where they can select the period and just see how the diesel engine is used. Is it used in overload or in underload conditions? And we can provide insight in real usage during a specific mission or a specific period. And this is already quite helpful. So we often want to develop very advanced analytics, but just giving the simple insight on how you use a machine is very valuable. And I think this step we often overlook also in research projects maybe, but also as companies. So we want to develop very advanced algorithms, but this simple tool gives a lot of insight to the crew. So crews are now coming to us to get more insight in, can you give us some insight in the machinery? Can you give insight in how we operate our diesel engines or the diesel generators? We'll give another example later. So one step ahead is defect detection. So in this example, we looked at the main the bearings of the main diesel engines, and we tried to see if we can find errors that occur due to high temperatures in the bearings. So we can signal, we can measure the temperature in the bearings and compare the measured temperatures with the temperatures that we should expect given a certain operation that we do. So we compensate for usage, and in this example, we use multiple linear regression and statistical process control to process the readings. And here we were able to detect a failure, I think 200 hours before the failure really occurred. So this is, of course, hindsight, but we hope to be able to use this analysis in the future to give the maintenance engineer indication of errors that might occur in the bearings. So this is an example developed by one of the students we have at the Data for Maintenance. So we have, I think, now 6 students. And of course, we develop a model to a certain level, which is not perfect for usage every day. So we also have now a PrimaVera project student, Esmee Steins, who is now developing more advanced statistical monitoring to improve this method that we have developed and see if we can detect the failure maybe earlier or make life easier to that we don't have to train the model by hand, but it will train itself. Try to see if we can use other statistics, try to see if we can use different statistical models to detect different types of errors in the bearings. So this is very valuable to experiment with different types of approaches for us. So another thing, this with linear regression is like maybe a white box model. And we also try to experiment with black box models. So one of the students is working on neural networks, long short-term memories, and she is looking at anomalies in the diesel engines, and she tried to just feed the model, I think 60 sensors or something related to the diesel engine, and try to see if she can detect anomalies. Well, she has already shown that she can do that, but she also now is developing some sort of warning table that gives the maintenance engineer insight in which sensors cause these anomalies, so they can do something of a diagnosis and plan a new course of action. So that means maybe you have to inspect. Some jets are flying over, so we will reduce the sound. So this warning table helps the maintenance engineer to get a diagnosis, plan a course of action. And in the bottom left figure, we can see the anomalies in the time, and you see a lot of red lines. It doesn't mean we have a lot of failures, luckily, but we see a lot of anomalies which can indicate an upcoming failure. So also, before this slide, maybe also in the PrimaVera project, we're also trying to see how we can combine the white and black box models. So can we use physical knowledge together with the data. And also the research of Luc Keijzer is very helpful to see how we can combine these models and use some kind of ensemble methods for a diesel engine, because you can imagine that there are many failure modes, and not one model will probably give us all the details. So we have to combine all these models to give the best insight to the maintenance engineer, so we can detect all the failure modes that are relevant to us. So one other thing is, as Bart already told, fuel efficiency is very critical for shipping, and it is also a big potential cost saver. So if we can give the crew insight in the most efficient sailing speed, we can possibly reduce a lot of fuel usage and also reduce the CO2 emissions. So what we try to do is, by using the ship data, combining this with the weather data that we can have from a database, maybe we can make the fuel consumption curve and give the crew insight in the most efficient speed, but also in the propulsion configuration. And one of the things that we have seen is that when we build a ship, that we don't have the best insight in what's the most efficient sailing speeds. And with the data, we can get a lot of insight from to the crew and give them insight in the propulsion configuration and also the speed, also routing advice. And this potentially helps saves us a lot of money and reduces also our CO2. So that's also why we joined Ocean 61, where we do data analysis for multiple ships, also commercial ships. We help the crew to reach their CO2 ambitions, and where we focus on social and behavioral components. So this match or this game is built up in 3 phases, where we first let the ship, the crew, do their best and see what they can reduce by themselves, and then we feed them some insights from the data. So, for example, we show them the fuel consumption curves. Left above, right above, we give them insight in the efficiency of diesel generators, also on the loading of diesel generators. So you can imagine that if you increase the load on the diesel generator, it's often more efficient. But what you often see on ships is there are multiple diesel generators installed, and the total load is divided on all the generators, and they all have a low load, and that's not very fuel efficient. So possibly you can increase or improve your usage and think of new ways to operate. So also on the right bottom there was a ferry, a Danish ferry, and it's totally different operation than a naval ship. So for us it's very interesting to look at their data and see how we can improve going from A to B and from B to A 6 times a day. So this is an example that we show that one trip was with 13.5 knots and the other way around was with 12 knots, and we can show how much fuel difference that costs. So quite interesting. They also won this race actually last year. But as Bart already told, we cannot do this on our own. So last year we organized a hackathon with 31 participants from also industry, also universities, and we asked them to come up with ideas to give the crew advice on how to improve their sailing. And in the left bottom you see the eco-friendly sailing assistant that won this competition, which gives the crew advice in changing the course or changing the settings. We wrote a small paper about that, and we are now developing optimal ship routing. For example, if you cross the ocean, there are multiple routes that you can take, but if you include the weather forecasts and your ship characteristics, I think you could save a lot of fuel. And that's also why we are developing some kind of eco button that we want to install on all our ships. So, but this final phase, also one of the work packages of PrimaVera, is how can you do now the maintenance decision making? We've shown that we can develop some interesting algorithms, but the most important step is getting this algorithm to the user. So how would this user receive some advice? So we want to go from the left, where the pigeon is saying you have one incoming failure, maybe on to the right, but we still don't know where we want to go, because we have to ask also our technicians and also respect their past and how this organization is shaped to give them the best option which works for them. So that's also one of the students, Bart, who's working on that to see how we can develop and present the outcomes of the algorithms best. So we hope to have given you a short overview of what we're doing, and we want to welcome you aboard and join this journey together with us and towards more predictive maintenance. Thank you very much.
All right. Thanks a lot. Very nice presentation, I think, at least. So that's worth a round of digital applause, I think. So at least from my side here. Yes. Yeah. Are there any questions from someone in the audience? And maybe, sorry? Yes, I see a hand.
Yeah, my camera was also not on. Yeah, a question for both of you is, given this focus on informatiegestuurd optreden, which is a strategic choice for the defense ministry or organization in the Netherlands, does it mean that when new equipment is bought, that was much more attention already for what is exactly the information that we want to collect from this equipment during the operation? Do you already think beforehand on sensors and, yeah, say the data infrastructure to collect the data on a structural basis? Is that included already, or how does that work?
Well, I would say that's ongoing. And we're using this space in experimenting with the ships which are already in service to see what we would need additional to what's already installed now. And that's in terms of sensors to detect failure mechanisms, but also to make sure that the data is already pre-processed on board. At the moment, we transport the data to shore every 3 months and by exchanging hard disks, and we need much more actual data to be able to look at predictions. If you look at a forecast of a few hundred hours, well, then every few months data is not enough. Then you only can detect the failures hindsight. So that all needs to happen on board. And we're working with industry, with Damen, RH Marine, for instance, so that they are enabled to understand what we need, that their R&D is focused on our needs. We gain maintainability from that, and we think that industry gains system development from it, so that they can market that also to other customers. Because our data is, of course, secure, but the analytics can be marketed elsewhere because that's generic.
Yeah. And do other countries also have this strategy that they in the future want more, yeah, information controlled, I don't know what, operations?
Yeah. Maybe a nice example is from the Oceans 1 challenge, where we did some analyses for a Danish frigate, and they were very well overwhelmed by the advice we gave back because their organization could not do that yet. So we try to work together with them, but yeah, of course, that's a growing process also for them. And what we often see is that for many crews, it's quite new, actually, that there are so many sensors aboard.
Okay.
I think it's a worldwide development, and I'm sure other navies do this as well, and also civilian companies. But well, we want to develop it for ourselves because we want to understand it. We want to know what influence it can have on our operations.
Yeah, thank you.
Let's see. So and by M. de Graaf. Sorry.
Yes, this is Maurice de Graaf.
Maurice. Sorry.
Yeah. Thanks for the nice presentation. I also now see that this picture is a question mark, so that's also it took some time. There, you presented a neural network-based way to detect failures, and in how far have you been able to? I've seen, say, some failure predictions, but were these actual failures? Was it also kind of confirmed failures, or was it more like, say, just a prediction?
No. What we have this of course one of the challenges is to verify the outcome. That's correct. But this network or this algorithm has shown some warnings. So in the hindclass data, and we have been able, and still trying, but been able to verify many of these warnings. And we try to see if there was actually happening something on that specific timestamp. And that's of course one of the challenges, that often the event data which is registered in an ERP system is often not the same quality as the sensor data, because the sensor data is very high quality. It has one reading every second, and this ERP system data doesn't include everything. So not every small malfunction is registered. But of course, this network might be able to indicate that something has happened. So we're now actually calling people, did you see something on that day? And yeah, that's of course very difficult, because this data is between now and 4 years ago. So that's quite challenging. But we have already been able to verify some major events, which are of course registered in the ERP system, that we were able to detect with this network. Yeah.
Okay.
But we see this as a promising approach. However, it's not in the maturity stage that we are now. Actually, we want to try to develop first Whitebox models, and only in the later stage this kind of models, because I think it's harder to show this to maintenance engineers and to gain their trust. And also, if it's saying something which is completely incorrect, yeah, it's hard for us to see that. But well, as the Dutch say, trouw gaat ter vaart. So we have to be careful with that. But this was maybe a student who was capable of developing such methods that walked in our office. So yeah, we are also just trying and experimenting. Yeah.
Okay, well, nice to know that. Thanks. Yeah.
Okay, I see a next question by Marcel van der Heijden.
Yes, thank you, Bart and Wieger, for the presentation. I've seen some earlier examples, of course, of the presentation and the data as well. And I noticed a minor shift towards maintainability, where we have examples on data for maintenance. And I see you changing the subject a bit to maintainability, which would be more of a design choice than, let's say, a life cycle event. Do you have any plans on continuing this? Maybe feeding the data you have towards design choices?
Definitely, yeah. And I think that works two ways. I think we can use current data to influence design choices. And secondly, the design choices should be such that in the future it will be easier to maintain. And maybe I haven't used the word maintainability in some previous presentations, but it's actually always been in the goal of the 2030 aim for the Navy, because the new ships come into service this decade.
Yeah, I would totally agree, and I look forward to our cooperation.
Yeah, of course, both ways.
So I actually also have one question myself, if I may. So I was wondering, most of these methods or algorithms that you presented, they seem to be for individual chips, right? Do you, for example, even see potential at some point to generalize these methods such that they can be used for multiple chips, or is the data that's monitored for different chips just too different for that?
Maybe two reflections on that. What we often see now, what we learn is that the model is suitable for many chips or installations, but you have to retrain it for every specific installation. So, for example, the model of the diesel engine that works for diesel engine 1, but you have to retrain it for diesel engine 2 because it's a totally different engine. And even if you do maintenance, the model is wrong. So doing maintenance changes the physical behavior in the machine. So between two totally similar machines, there can be such a different behavior inside that the model sees all kinds of strange things which are not there or might be there. Not me to judge that. But I think the approaches that we develop are that we can use those approaches for all kinds of machinery. So even the example of the multiple linear regression, I think there are other applications that we can use the approach for, but then you have to retrain or redevelop the model.
Yeah, indeed. No, makes sense. Indeed. Let's see.
And that's additionally maybe an important question also for PrimaVera, because if you use Whitebox models, you need to do more tuning, even more tuning than on the black box model. So how can they work together? How can you use black box as an indication to employ Whitebox models for more specific diagnosis or whatever? That's the question.
Yeah, no, indeed. Yeah, makes sense. Yeah. Let's see if there are any more questions. All right, so if not, thanks again, Bart and Wieger, for the very nice presentation. So the next, and I think also the last colloquium before the summer, is in 4 weeks, on the 30th of June, and will be given by Errol Zalmijn. So hope to see everybody there again, and have a nice afternoon and enjoy the remaining hours of the hot sun.
Thanks for hosting, Tom.
Thanks. Thank you.
And all attendees.
Bye, everyone.